Okay, just to show you some of the dizzying versatility and power of recursive, constructions, let me show you how to use recursion to define now more complex things like sets. So we're going to talk about recursive sets and structures, recursive structures. In particular, we're going to talk about trees. Okay. So recursive sets / structures. Okay. In particular, I'm going to give you now a definition of the natural numbers, okay, and this definition uses recursion, and so we'll use that, to illustrate the prototypic sort of recursive definition of a set. Okay, so finally, I'm going to define for you in a very formal way the natural numbers. Okay, so the natural numbers. Okay, so this is a set. So N is a set. Okay. And what I'm going to do is I'm going to give you a sort of a recursive procedure for constructing this set, one element at a time. Okay, but first I have to tell you at least one thing that's in the set. Okay, so first I'm going to tell you at least one thing that's in the set. Okay, so the number 1 is in my set, which I'm labeling this blackboard bold N. Okay, so this is called the base, the basis, or the basis. Okay. Establishes that at least something is in your set. Okay, good to know. Now, what I'm going to do is I'm going to give you what's called a constructor rule. Okay, now what does this do? What the constructor rule does is it says, if you know that something is in your set, is there a way for you to get something else that's in your set? Okay, so that's why we call it a constructor. Can you construct new things that are in your set? Okay, so the constructor or the constructor rule, okay, is going to be very simple. So we call this the constructor. Okay, so the basis clause, the constructor clause, which says, I'm going to say that if X is in my set, whatever it happens to be, then X plus 1 is in my set. Okay, so that's a rule. It's a constructor rule. Okay. Now, for reasons that you'll see shortly, we add one more sort of clause, which basically says it's called the minimality clause, or sometimes it's called the extremal clause. Okay, so minimality. Okay, basically says nothing else is in N. So in other words, if something is in N, okay, then it must either be coming from the basis case or it must have been constructed using the constructor rule. Nothing else is in N. Okay, so let's see, what is N? Okay, so what is N? Well, we know that it has 1. Okay, but now we can apply the constructor rule. Because it has 1, we know that it has 2. Because it has 2, we know that it has 2 now. Because it has 2 is in N, we know that it has 3. Okay. So sometimes we say that 3 is the successor element of 2 and 2 is the predecessor of 3. But okay, forget about all that notation. Because we know it has 3 is in N, so therefore 4 is in N. 4 is in N, so therefore 5 is in N. You see, this stream of construction is sort of like a stream of consciousness. It never ends. It just keeps on going. 5 is in N, so therefore 6. 6 is in N, so therefore 7, and so on. Okay, but now this and so on is not in this definition. That's just how I choose to write blah, 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 fill in the blanks. Here is the formal recursive definition of N. And, with the recursive definition of sets or anything in general, when you define a set of objects recursively, basically, you have to have these 3 conditions. You have to have a basis. So you have to tell me that some things are in the set, okay? Because I can't construct out of nothing. So you have to give me my basic elements that are in my set. Okay, now you tell me how to get more complex elements from my basic elements. Okay. And this last clause looks like a formality. Basically, you're saying nothing else is in N. Okay, so now, I'm gonna show you why we have to have that clause. Okay, but first let me show you. Okay, so how do I know that 6 is in N? So, well, let's take 9. Let's take the number 9. Okay, and let's take the number 7.5. Okay? And I'm going to ask, is 9 in n? And everyone, I know, they're all jumping up and down, saying, yes, 9 is in n. Okay? And how do we prove it? Well, the way we prove it is we have to construct it. We have to show a derivation of 9. And here it is. Well, we know that 1 is in n. Okay? And by rule 2, by the constructor, we know that 2 is in n. And then by the constructor, we know that 3 is in n. And by the constructor, so I'm putting rule 2 in here, we know that 4 is in n. And by the constructor, we know that 5 is in n. And, you get the picture. It's kind of a boring picture, but hey, let's complete it. Okay, 7 is in n. And by the constructor, 8 is in n. And by the constructor, 9 is in n. And now we've got our 9. Okay, and this is an example of what we call a derivation. So at every step in the derivation, we apply the constructor rule. Okay, and it must be the case that you can only apply the constructor rule to things that you have previously derived. Okay. This is a valid derivation. Now 7.5, you try to find a derivation for 7.5, you won't be able to find one. Okay. And in fact, you won't be able to find one for anything that is not in the set that we formerly knew as the natural numbers. Okay. Formally. Now also we formally know it as the natural numbers. Now we have a formal definition. Okay. So why do we need this minimality clause? Well, think about the following set. The real numbers. Okay. Well, is 1 in the real numbers? Yes. The real numbers are huge. Okay. And 1 is in the set of real numbers as we know and love them. Okay. What about, do we know that if something is in the real numbers, is the successor, is that number plus 1 in the real numbers? Yes. 7, if this is remember, this is an implication. It doesn't say x is in the real numbers. It says if x is in the real numbers, then x plus 1 is. So if 2.5 is in the real numbers, is 3.5 in the real numbers? Yes. So the real numbers satisfies 1 and 2. Okay. Satisfies 1 and 2. But it has other things beyond this. Okay. And so that's why the real numbers this is not the definition of the real numbers. Because it's not the set that contains only this element and those elements derivable using the constructor rule from the base elements. Okay, it has other things in it. Okay, and for the same reason, you can consider this set, let me call this A, is equal to 1, 1.5, 2, 2.5, 3, 3.5, and so on. Okay, this set satisfies 1 and 2, because 1 is in there. Okay, and if whatever is in here, if something is in here, its successor is in here. So 2 is here, 3 is here, so the 1.5 is here, its successor is here. So all the successors are there for any element in the set. So it satisfies 1 and 2. But it has other things. So 1.5 cannot be derived. So this set is not the natural numbers. Okay, and technically you could imagine that another way of saying this is the natural numbers is the smallest set that satisfies those two properties. And that would rule out A, and that would rule out the real numbers. Okay, so there. Formal definition of the natural numbers. Let me give you another recursive definition, and let's see, what have we defined? And in this case, we're defining a set of strings. Okay, and so let's define the set of binary strings. Okay. Now, first of all, I want to remind you, which you may not be familiar with, just like the empty set, there's what we call the empty string. So the empty string is the string that contains nothing. Now it's hard to write down a string that contains nothing, so we have a notation for that. We call that, epsilon. Sometimes people call it lambda. Okay, we'll call it epsilon. Epsilon for the empty string. Okay, just like the empty set, which contains nothing. So here's a formal definition of a set of strings. Let's call this set of strings sigma star. I don't know. I'm calling it sigma. Well, I can call it whatever I want. You might say, why do you call it sigma? Why do you put the star? Okay, well, we'll, just to be consistent with what we do later on, far along in the course. Okay. So, 1, epsilon is in this set sigma star. Okay, so I'm telling you something that's in the set. Well, that's a pretty stupid thing that you're telling me. The string that is empty, that contains nothing, is in your set. Yeah. Okay, but it is a proper string. It just has nothing in it. Okay? It's a binary string of length 0. Okay. Now, if X is in sigma star, then, now I'm going to use this notation called concatenation, or, think of it as, prepending or appending. You can, when you append a string to another string, that's an example of concatenation. When you prepend a string to another string, that's an example of concatenation. So we will say X is in sigma star, then X concatenated with 0 is in sigma star. Okay. And let's call that, and X concatenated with 1 is in sigma star. Okay. So this is a complex rule. It says that if ever you find something in sigma star, then you can append 0 and you can append 1, and that's also in sigma star. So let's see what is this sigma star. So sigma star is this set that has the empty string. Okay, but now you can concatenate onto the empty string 0 or 1, because the empty string is in sigma star. So I get 0, I get empty plus 0 is just 0, and empty plus 1 is just 1. So I get 0 and 1. Okay, now I have 3 things that are known to be in my sigma star. Well, we already dealt with that guy, so let's see what this guy gives me. So this guy gives me, 0, and I can concatenate, I can append 0 and 1, so I get 0, 0, and 0, 1. And this guy gives me, because it's in sigma star, this guy gives me 1, 0, and 1, 1. Oh! Okay, now what do these guys give me? So I found now, 4 more strings that are in my set. What do these guys give me? Well, this guy, 0, 0, gives me 0, 0, 0, and 0, 0, 1. And what does 0, 1 give me? 0, 0, 0, 0, 1, 0, and 0, 1, 1. What does 1, 0 give me? 1, 0, 0, and 1, 0, 1. And what does 1, 1 give me? 1, 1, 0, and 1, 1, 1. And you can continue. And you should be able to hopefully, at least, intuitively convince yourself that every binary string will sooner or later pop up in this set. So this is the set. Sometimes we call this the set of all finite binary strings. Okay, now, what about the string, 1, 1, 0, 1? Okay, that string in here. So if this string is in here, we should be able to give a derivation. Oh, and by the way, nothing else. Now, usually we are lazy. Okay, this minimality clause, it doesn't really, it doesn't seem to be changing from one definition to another. So we usually just leave out this minimality clause and we just, default it's there. We always assume that we're defining the smallest set with properties 1 and 2. Okay? So if 1, 1, 0, 1 is in my set, I should be able to give a derivation. So here's a derivation. And now, pause the video, try to get the derivation before me because I'm going to give you a speed derivation. Okay? I'm going to give it to you in 1, 2, 3, 4 seconds. Okay, so here. So epsilon is in my set, and because epsilon is in my set, epsilon 1 is in my set because I can add 1. But if epsilon 1 is in my set, then, so this is rule 2. If epsilon 1 is in my set, then I can add 1 to that. So epsilon 1, 1. And if epsilon 1, 1 is in my set, then I can add 0 to that, epsilon 1, 1, 0. So that's rule 2. And if epsilon 1, 1, 0 is in my set, then I can apply rule 2 again and append a 1. And I get epsilon 1, 1, 0, 1. Boom. But epsilon is the empty string, so this is really just nothing. Okay, so 1, 1, 0, 1. There's the derivation of 1, 1, 0, 1. That proves that 1, 1, 0, 1 is in my set because it can be derived. Okay, so quick intro to recursive definitions and 2 examples. The recursive definition of n. So we now have a formal definition of no ... needed. Nice recursive definition. Okay, and we have a formal definition of the set of all binary strings. Okay, no ... involved. Okay. So let's go and discuss recursive structures. In particular, that very important structure that we use to build data structures in CS called a tree. And specifically, we're going to talk about, rooted binary trees. So I'm going to give you now a formal definition of rooted binary trees. Trees are very important in computer science. And I went to the trouble of listing, where are trees used? And my list became huge. So I truncated it. But let me just read to you sort of part of the list that I got. Okay, search trees, game trees, decision trees, compression trees, so for compressing files, multiprocessor trees. So we arrange processors on a tree and then distribute tasks among the processors, and they communicate along a tree communication structure. Okay, so multiprocessor parse trees, compilers parsing HTML to render it as a web page. Those are parse trees. Expression trees, evaluating arithmetic expressions. So we formulated expression trees. Ancestry trees. So before computer science, we all wanted to know what does our history look like, and you go and say, well, I have two parents and they have two parents each, and then so on and so forth, and brothers and sisters and so on, and this forms an ancestry tree with you. Even though you appear at the bottom, technically you are the root of this tree. Okay. Organizational trees in companies and so on and so forth. So trees are fundamental in terms of what we use them to do in computer science. So let's at least have a definition of what is a tree. And I'm going to give you a formal definition. So rooted binary trees. Now, the history of trees is interesting. So, a mathematician by the name of Arthur Cayley discovered trees. Okay? And how did he discover trees? Well, a chemist came to him and said, I've got this interesting phenomenon. I can measure the sort of the chemical composition of various organic compounds, and so there's methane, so CH4, C2H6, C3H8, and C4H10. Okay. And so these are different organic compounds, and he says this thing, it only comes in one structure. This thing only comes in one structure. But I have two different mixtures that both have the molecules both have the same chemical composition, but they behave differently. So they must be different molecules, even though they have the same chemical composition. Okay. And so then Arthur Cayley was trying to figure out mathematically how could this be the case, because people thought that chemical composition at that time determines everything. Okay, your properties are a function of just what you are made of, not how it's put together. Okay. And then Cayley said, well, what if it depends on how it's put together? And he thought of the simplest way of putting things together. And so he constructed a tree for this organic compound called methane. He said it's CH4. So, carbon is, think of carbon as the root. And then this guy is C, and hydrogens, CC and hydrogens. Okay. So he started representing the molecule, not just in terms of its composition, but also using its structure. And then he came to this, and he found there's only one structure that is consistent with C3H8. Okay, and then when he came to butane, this is propane, this is butane. Propane you should know, because that's what you use in your camps to light the gas and so on and so forth. Okay, and when he came to butane, he said, there are two structures of this form that are consistent with that chemical composition, and thus was born trees, because these are all trees. And so he's, and that was also in some sense the birth of the sort of notion that it's not just your chemical composition, it's not just what you are made of that determines how you behave, it's how the things you are made of are put together. And think of society. Okay, think of society. We've got a bunch of people, but society functions differently if those different people are interconnected in different ways. So structure plays a huge role. And in the functioning of things, in our ability to build data structures. I mean, it's just unbelievably wonderful how structure, things with the same composition, but different ways of structuring them together have totally different properties. Okay? And the most basic kind of structure is the tree. Okay? And, with that generally, irrelevant aside, let's get back to the formal definition of trees. Great. So the rooted binary tree is going to have a recursive definition, just like the sets, natural numbers, and binary string. Okay, so step one. Tell me something that's a tree. And just like the empty string, we're going to define this thing called the empty set, the empty tree. So the empty tree, epsilon. Okay, epsilon is, okay, so epsilon, and I'll define this set of rooted binary trees, I'll call it RBT for rooted binary tree. So nothing, the empty tree, is a rooted binary tree. Okay. And, Now I'm going to give you, I'm going to continue the definition pictorially. Okay, so because we're trying to define structures, and it helps to use sort of a pictorial definition. Now we can define this formally with with graph notation. Remember, graphs are the right kind of discrete object when we have objects and links between them. So we can define this using a graph notation, but pictorial is going to suffice. Okay? So I'm going to tell you how to build new trees from old trees or things that are known to be trees. So if T1 and T2 are two trees, if T1 and T2 are two trees, okay, then what I can do is I can connect them. Okay, so they are rooted binary trees. Okay, so what it means is, okay, so envision in a rooted binary tree that every tree has a special object, which we call the root. Okay, and so these two trees have these special objects which are called roots. So let me draw them like this. So this is T1 and this is T2. Okay, and they each have roots. So So you should have seen trees before, so this discussion should be familiar, but now I'm trying to put it into a formal recursive definition. So you have two trees, each of them have roots. Okay. The only case where they don't have roots, is if they are already empty. So there's no root to be had here. But if they have no roots, then they have no roots. That's also fine in the definition. But the important part of the definition is when the trees have roots. Then what I can do is I can construct a new tree, i.e. a new structure, in which I have my T1 and I have my T2, okay, which had their roots, but now these no longer become roots, they're no longer roots, and I connect those two roots to a new root, okay, and so this tree T1 and this tree T2, when connected together and their roots are connected together and link up to a new root, this is a tree. So this is a tree. Now, I could be more complete and say, I can also switch the order. So this is also a tree. T2, T1, that's also a tree. It's not necessary because I can always, reverse the order in the if here. Okay, so this is also a tree, okay, where you connect the roots to the new root. Okay, that is also a tree. And nothing else is a tree, but I won't bother saying that here. Okay? So, let's see if, we can construct some trees. So what is this set of rooted binary trees? Okay, so let me show you. Let's start with the epsilon tree, which is nothing. Okay, so now, this is the only thing I know at the moment. So I'm going to use my constructor. I'm going to use my constructor rule. Okay, and every time you generate a new tree, you're using the constructor rule. So let me not say what, rule I'm using. Instead, above here, I'll put what T1 is, and below here, I'll put what T2 is. So T1 equals epsilon, T2 equals epsilon. So it's perfectly fine for T1 and T2 to be the same beast. Okay, so nothing. So what do? I connect nothing to the root. I connect nothing to the root because T1 and T2 are nothing. So I connect nothing to the root, nothing to the root. So I end up with a root. Okay, that has nothing. So it's just a root. So a single root. Sometimes we'll just call this the single root node. Okay, so this tree has size 0, size being the number of nodes. This tree has size 1. Okay, let's keep going. Now it gets complicated. Okay, actually, I can now construct 3 new trees. Okay, and this is where things get interesting. Okay, what are the 3 new trees? Well, I can construct 4 new trees. Okay, so here. Okay, now I can set T1 equals epsilon, T2 equals my root. Okay, what do I get? So I'm going to take T1 and T2 and connect them both up to a new root. Okay, so I get a new root with nothing here and a single node which is T2. Okay, I can flip the roles of T1 and T2. So I can make T1 my single root and T2 is epsilon. And now what do I get? I get this guy. So I consider those to be different trees. Okay, so the order, so these are ordered trees. The order in which you consider these are called the child subtrees. So this child subtree, and this tree and this tree could in general be different. It's only when these two guys are the same that we say that they're the same tree. Okay, so 1, 2. Okay, so this is when one node is your actually. So there are in fact only three. And now I can set T1. Okay, so T1 equals the single root, and T2 equals the single root. Okay, and what do I get here? I get my root of my parent. These are what these trees are called parent trees, and this is called the child tree that's constructed, and so it's connected to 2. Okay, and we can keep going. So let's keep going. So now we have some new trees. We have this tree and this tree. So let's, for example, apply the constructor rule from here with this guy and that guy. Okay, so from here we can apply. Let's say let's consider both cases. So let's consider T1 equals the single root, and T2 is equal to this guy. Okay, T2 equals this. Then what do we get? So we get our new root. Okay, connected to T1 and connected to T2. Interesting. Okay. And if we flip the roles of T1 and T2, then T1 is equal to this guy, and T2 is equal to this guy. Okay, then we get a new root. Okay, it's connected to this guy. It's connected to that guy. Okay, different looking tree. Okay, interesting. So these are all different trees, and you can play around with this definition and construct more and more trees. So let me ask some questions. Okay, and these are challenge questions. So here I'm gonna draw a structure. Okay. Is this an RBT? Question. Is that an RBT? Okay. And let me give you another structure. Very similar. Okay. Okay, so another very similar structure. Let's say that I add another link. Let me put it in blue. So to highlight the difference, I'm going to add this link here. Okay. Is that an RBT? Is this an RBT? Okay, so question mark. Challenge questions. Okay, so in order to convince me that these are both RBTs, what you need to do is just give me a derivation. So for example, we say that I've derived this guy, so we know that that's an RBT. So can you give me a derivation of this guy? Okay, and can you give me a derivation of that guy? Okay, now I'm going to give you some hints. Okay. This is an RBT. Okay. And the way you would show me, the way you would convince me that this is an RBT is to give me a derivation. I'm going to claim that this is not an RBT. I'm going to claim that that second one is not an RBT. And now you should ask yourself, really? Are you sure? How do you know? Okay. Because what am I saying? Look at how complicated derivations with trees is. And what I'm saying is that there's no way, with all the ingenuity on earth, using this formal definition of RBTs, there's no way to construct a derivation that's going to produce that. Okay, but there are so many different ways to construct derivations. How do we know that you cannot produce that? Okay. And how do we know that we can produce that? We can just show a way to do it. But showing that you cannot produce that seems like a daunting task. So I'm going to end with some questions. Okay. They mostly, are relating to trees. Questions. 1. How do we know that this guy here, let's call this, tree 1, let's call this guy tree 2. How do we know that tree, I'll put it in quotes, 2 is not in the set RBT. It's not a rooted binary tree. How do we know that? And there are lots of other definitions of trees. Okay, there are lots of other definitions of trees. So for example, there's another definition of tree which says that, remember graphs. So if you think about this graph, we say that that the nodes are connected, because if I start at some node and I move, I can move along edges and get to every other node. Okay, so and this is an example of what's called a cycle. Okay. And so there's another definition of trees, which is that a tree is a connected graph that has no cycles. Okay, so there are other common definitions of trees, more general trees, not just rooted binary trees. Okay, and do those definitions sort of match to this definition I've just said, and how would we prove such things? So yes to all of that. Okay, the definitions match. We're not defining something new. Okay, and there are ways to prove all these things. And so the next lecture is going to discuss, how to prove things about recursively defined sets and structures. Okay, but before we leave, I just want to leave you with a couple of, thoughts. Okay, so parting gifts, parting thoughts. So parting thoughts. Okay, so one, recursion is very powerful. Okay, and what I've shown you in this lecture is sort of some of the many uses of recursion. We can define recursive functions. We can define recurrences. Okay, we can define recursive programs, and recursion and recurrences for the runtime are important for analyzing how quickly those programs run. We can define recursive sets. We can define recursive structures. Okay, so powerful. Okay. But I also want to say that recursion is your friend if you are careful with it and you prove that your, let's say, recursive programs or your recursive structures have the properties that you think they have. Okay, so recursion is your friend if you do it right. Okay, but it's possible, so it's a deadly enemy. It's a dangerous enemy if you make even small mistakes. So you have to be very careful with recursion. It's powerful. It's, it's just an unbelievable tool for solving problems. But if you make even small mistakes, in a recursion or a recursive definition or what have you, you could get something totally different. Okay. And exercise 7.4 shows you a little bit of that. So I gave that to you as one of the practice exercises. So this is an exercise where, you consider recursive functions and then slightly change them here and there and see what that does to the recursive function. You can just change one number, and all of a sudden you go from a nice recursive function to something that's just, useless. It's just a zero, let's say, everywhere. Okay. So powerful. It's your friend if you do it right. It's your enemy if you do it wrong. Till next lecture.